Now, a semiconductor without any artificially added impurities is called an intrinsic semiconductor. Silicon and germanium, the two most commonly used semiconductors, are intrinsic semiconductors. Both silicon and germanium have 4 valence electrons. In crystalline form, such silicon and germanium atom uses its valence electrons to form 4 covalent bonds with 4 neighboring atoms. At 0 Kelvin, all the covalent bonds in the crystal lattice of an intrinsic semiconductor are intact. Therefore, at absolute 0 temperature, there are no free electrons to occupy the conduction band, and the intrinsic semiconductor behaves like an insulator. However, at higher temperature, some electrons gain enough thermal energy to break free of the covalent bonds in the crystal lattice. These free electrons move to the conduction band, and the material starts behaving like a semiconductor. Note that each electron that moves to the conduction band leaves behind a vacancy in the valence band. This can be visualized as breaking of a covalent bond, where an electron becomes free and leaves behind a vacancy in the covalent bond. An electron breaking away from a covalent bond takes away a unit negative charge with it, leaving behind a vacancy with an assumed unit positive charge. A vacancy with a unit positive charge in a covalent bond between atoms of a semiconductor is called a hole. So whenever a covalent bond is broken in an intrinsic semiconductor, a free electron and a hole are created. We call this an electron-hole pair. Therefore, in an intrinsic semiconductor, the number of free electrons is always equal to the number of holes at any given moment. Consider a hole at position 1 in the crystal lattice of a semiconductor. An electron from position 2 can jump to occupy the hole at position 1. This in turn creates a hole at position 2. An electron from position 3 can jump to occupy the hole at position 2, effectively creating a hole in position 3. As a result of this jumping of electrons, the holes appear to be moving in the opposite direction across the crystal lattice of a semiconductor. Note that the movement of holes occurs due to the movement of electrons across covalent bonds and not because of the movement of free electrons. Thus, there are 2 types of moving charge carriers in the crystal lattice of a semiconductor: negatively charged free electrons and positively charged holes. When an electric field is applied across a semiconductor, the free electrons move towards the end connected to the positive terminal and generate an electron current denoted by IE. The holes shift towards the end connected to the negative terminal and generate a hole current denoted by IH. Total energy through the semiconductor is given by IE plus IH. If a free electron collides with a hole, it fills the vacancy in the covalent bond without generating any other hole. This is called the process of recombination. Under thermal equilibrium, the rate of generation of free electrons and holes is equal to the rate of their recombination, so the density of the charge carriers remains constant.